You know, in the world of power electronics, there's this quiet revolution happening. And it's all because of a material called silicon carbide, or SiC for short. It's really the key to making everything from our electric cars to massive data centers way more powerful and, believe it or not, incredibly efficient. So let's dive in and see how.
So, here's the big question, right? This is the fundamental challenge that engineers everywhere are grappling with. We want more and more power for our data centers, for our EVs. The demand is just exploding. But at the exact same time, we have to slash our energy waste. And the answer isn't just to build bigger systems. It's about making the heart of those systems, the components themselves, smarter, faster, and a whole lot more efficient. And that is exactly where our story starts today.
All right, so here's our game plan. First, we're going to talk about why this change is so necessary. Then, we'll get to meet the star of the show, a brand new SiC module from BASiC Semiconductor. After that, we're going to put it head-to-head with the old guard in a data showdown. We'll also look at the system that really unlocks its full power, and finally, we'll see how this tech is literally powering our future.
Okay, let's set the scene. We are truly in a new era for power electronics. And efficiency, it's not just some nice-to-have buzzword anymore. It is an absolute must. Think about it. Every single bit of energy that escapes as wasted heat is basically a failure in the system. And those little losses, well, they add up incredibly fast.
For decades, silicon has been the undisputed king of semiconductors, right? It's powered everything from the phone in your pocket to the car in your driveway. But when you start talking about high voltage, high power systems, silicon is really starting to hit a wall. It just generates too much heat, it wastes too much energy, and honestly, it just can't switch fast enough for what we need today. The throne is basically waiting for a new champion.
And that new champion is silicon carbide. So let's meet the specific device we're looking at today. It's the BMF 540R12M-ZA3, a SiC MOSFET half-bridge module from a company called BASiC Semiconductor.
And here it is in its ED3 package. Now, this isn't just some plastic casing. You should think of it more like a suit of armor. It's been engineered from the ground up for the tough reality of high-power industrial settings. Every single design choice here is about one thing and one thing only, maintaining peak performance, even when the conditions get really, really rough.
But of course, the real magic is what's on the inside. This thing is built on BASIC's third-generation chip technology, which is engineered for the absolute minimum energy loss and the maximum possible switching speed. And that incredible speed is what lets engineers design smaller, more compact systems. And notice the focus here on thermal management. It uses these advanced materials like a silicon nitride substrate and a copper base plate. Together, they act like a superhighway for heat, just pulling it away from the sensitive parts to make sure this thing stays reliable for a long, long time.
So the specs sound pretty impressive, but how does it actually perform in the real world? Well, it's time for a data showdown. We're going to pit this new SiC MOSFET against the long-reigning champion of power electronics, the good old silicon IGBT. Let's see what the numbers have to say.
Okay, so here are two contenders. On the left, you've got the SiC MOSFET. This is the new school, the next-gen tech, designed for blistering speed and peak efficiency. And on the right, you've got the classic IGBT, the powerful workhorse that's been doing the heavy lifting for years, but it's fundamentally limited by a slower and, frankly, less efficient design.
Now, to make sure this is a fair fight, the source material lays out a simulation with identical conditions for everyone. We're looking at a standard buck converter, stepping 800 volts down to 300. And look, everything's the same. The power level, the current, even the heatsink temperature. This is a true apples-to-apples comparison. And the results? They are just staggering. Look at these bars. They represent pure wasted energy just lost as heat. The BASiC SiC module loses just 431 watts. Now, in the exact same conditions, the two competing IGBTs waste over 1,700 and 1,900 watts. That's more than 4 times the energy just thrown away. Let's be really clear here. This isn't some small, incremental gain. This is a complete game changer in efficiency. So what does that massive energy saving actually mean in practice? Well, it means you get a system efficiency of 99.58%. Just let that sink in for a second. Nearly every single watt of power that's going into the system is doing useful work. In the world of high-power electronics, a number like that, well, it's nothing short of revolutionary. But look, having a world-class engine,
isn't enough. You need a world-class driver to actually control it. See, the incredible switching speed of these SiC devices is their greatest strength, but it's also their greatest challenge. To really harness that speed safely and effectively, you need a specialized gate driver that's designed specifically for the job. And this is exactly why BASiC provides a complete engineered solution. On the left, there's our power module, and on the right, you see the 2CP0425TX driver board, purpose-built to control it. This isn't about convenience. It's about unlocking the module's absolute peak performance and, just as importantly, guaranteeing its safety. This driver is really the brains of the whole operation. It has its own custom chip, it delivers a powerful 25-amp peak current for super clean switching, and it's got a whole suite of protection features built right in. But I want to zoom in on one feature that is absolutely critical for these fast switching systems, something called the Miller clamp function. So, what on earth is this Miller effect? Okay, imagine a circuit where you have two switches working as a team. When one switch slams on really fast, that sudden change in voltage can actually leak over and accidentally nudge the gate of its partner, the one that's supposed to be turned off. Now, if that nudge is strong enough, both switches can be on for a split second, which creates a direct short circuit and, well, catastrophic failure. This diagram here shows that dangerous little gremlin, that parasitic current, IGD, in action. As the top switch, Q1, turns on, this current tries to sneak over and accidentally activate the bottom switch, Q2. So the Miller clamp, it acts like a security guard for the gate of Q2. It actively holds that gate down, creating a solid, low-impedance path to ground that ensures it stays firmly off. It's an absolutely essential safety system. Okay, so we've got a hyper-efficient power module, we've paired it with a smart protective driver, and we've seen the data. So now, where is this technology actually going to make a difference? Let's take a look at the future that it's busy powering right now. The applications are pretty transformative. For things like energy storage and solar, higher efficiency means you capture and deliver more power from every single solar panel. For the grid, it enables smaller, smarter transformers. And for electric vehicles, this technology is a triple threat. It directly translates to longer range, lighter vehicles, and just plain better performance. And you know what? It all comes back to this simple but incredibly powerful trifecta from the source material. Lower switching loss means you waste less energy. That lets you switch the device much faster. Switching faster lets you use smaller and lighter components, like capacitors and inductors. And all of that leads to a higher power density, which just means more power in a smaller, lighter package. And this really brings us to a fundamental shift in how we think about design. For decades, a huge part of power engineering was just damage control, right? It was about managing all the heat that was being wasted by inefficient components. But as technologies like silicon carbide get us closer and closer to 100% efficiency, those old problems they start to evaporate. The old rulebook gets thrown out the window. So we'll leave you with this question to think about. What becomes possible when you no longer have to design around waste, but can instead design for pure, unadulterated potential?